In today's video lecture, we're going to finish the packet of notes dealing with RC and RL transient circuits. The first thing we're going to do is revisit the problem that we just looked at. So last class we had this problem here where we had a change in the circuit at time 0. We had the 80 volt source switching into the circuit at time 0, and at the same time we had the 100 volt source turning off. And we solved for Vc of t and got the expression 20 plus 70 e to the minus t over 6 volts. This circuit is the exact same circuit. The only difference is we are not looking for Vc of t in this case. We are looking for IR of t. So if you think back to our algorithm, there are these two steps, step 2 and step 7, that we did not have to worry about before. Step 2 and step 7 apply only if the variable that you're looking for is something other than Vc or IL. In this problem, that's exactly the case. The variable we're looking for, x, is IR. Since it's different than Vc, we now have to worry about steps 2 and 7. So from before, we know what Vc of t is. Vc of t is 20 plus 70 e to the minus t over 6 volts for t greater than or equal to 0. We actually will need to use this result in solving for IR, as we will see now. So to solve for IR of t, we only need two additional pieces of information. The first one is from step 2. We need IR before the change in the circuit. So if you draw the circuit before the 80 volt source is switched in, we are in a DC steady state situation. The voltage across the capacitor is a constant, and the capacitor looks like an open circuit. The 100 volt source is there, 4 ohm, 12 ohm, 24 ohm, Vc, and we have this new variable IR, which is the current through the 12 ohm resistor. Well, it's pretty easy to see that IR at 0 minus is just Ohm's law. It's 100 volts divided by 4 plus 12 plus 24, or 40 ohms. So we get 2.5 amps. I should point out that after the change in the circuit at time 0, IR of 0 plus is not going to be the same as it is for 0 minus necessarily. Once again, for any variable other than Vc or IL, its value could possibly change instantaneously. We'll find out soon whether that's the case here. The other piece of information we need is from step 7. We need a general equation relating I of t, IR of t, to Vc of t for t greater than or equal to 0. We already have Vc of t, so once we get this general equation from step 7, we can just plug this value of Vc of t into that general equation to get a general equation for IR of t for t greater than or equal to 0. Turns out this is a fairly easy step in this particular problem. If you redraw the circuit after the change at 0, now this 80 volt source is present. The capacitor is no longer an open circuit, and the 100 volt source is off. And once again, we're looking for this current IR. Well, if you end up calling ground down there, the voltage at this point is Vc of t, which once again we have. The voltage at this point is 80 volts. So it's actually trivial to find this general equation. IR of t from Ohm's law is just the voltage at the coming from point, which is Vc of t, minus the voltage at the going to point, which is 80 volts, all over the resistance, 12 ohms. And once again, this is valid after the circuit changes at 0. So let's see what that actually evaluates to. So for t greater than or equal to 0, IR of t is going to be Vc of t minus 80 over 12. Once again, this part was Vc of t from the previous problem. You get minus 60 plus 70 e to the minus t over 6 over 12, or minus 5 plus 5.83 e to the minus t over 6 amps. So we can get our general expression for IR of t valid for all time. From step 2, we know that before the change at 0, it's 2.5 amps. We got that from the DC steady state part of the problem. And then from the step above, we see the value is minus 5 plus 5.83 e to the minus t over 6 amps for t greater than and equal to 0. Note, by the way, that IR of 0 plus, plug in 0 into there, IR of 0 plus is minus 5 plus 5.83 times e to the 0, which is equal to e 0.83, which does not equal IR of 0 minus, as we claimed was going to be the case. We can now plot this result. We see that we had 2.5 amps for t less than 0. At t equal to 0, all of a sudden, the current through that resistor changes immediately to 0.83 amps. And then it's going to exhibit an exponential decay and eventually get to minus 5. How long is it going to take? It's going to take 5 time constants. Once again, we're plotting this on a normalized time axis, and so this 5 here actually means 30 seconds. This is 6 seconds, 12, 18, 24, and 30. And it's going to exponentially drop from 0.83 eventually to minus 5. If you wanted to find the exact value after one time constant, what we know is that the current through that resistor is going to go from plus 0.83 all the way down to minus 5, and it's going to do 63% of that during that first time constant, leaving 37%. So 63%, 37%. And so we can calculate the value after one time constant. So IR of 6 is going to be the original value And notice we're not doing the value before 0, we're doing the value right after 0. It's the original value plus 0.63 times the final minus the original. You get minus 2.84 amps. In this problem, we're given the response, but we're given an incomplete circuit. So we do not know the value of the inductor in this case. We also do not know the two values of the voltage source. So if you look at the voltage source, if you were to plot this, for t less than 0, it's going to be Vs1. At time 0, Vs1 turns off, and instead we get Vs2, which could be higher or lower. We don't necessarily know yet. So V source is going to look something like that. But we don't know what the values for Vs1 and Vs2 are. Because we have three unknowns in the circuit, we need to gather three pieces of information from the plot. The three pieces of information are going to be the value of the current through the inductor at 0 minus, the value of the current through the inductor at infinity, and also the time constant. So the time constant, if you recall, when you have an exponential decay, if you extrapolate the initial slope, you can get the time constant. But before, we took that initial slope all the way down to the x-axis and said, okay, it would be at 4. But actually, we don't do that here. You don't take it down to the x-axis because this is a driven circuit. You take it down to the final value. Final value is 0.2, and so the point we take it to is this point right here. So we get that the time constant is 2 seconds. We could also get that from looking at how long it takes to settle to its new steady state value. It takes 10 seconds, which should be 5 times the time constant. For an RL circuit, the time constant is L divided by the Thevenin resistance seen by that inductor. So if you look at this circuit here and look at the Thevenin resistance, remember to find the Thevenin resistance, you set voltage source is equal to 0, current source is equal to 0. R Thevenin is now the parallel combination of 10 ohms and 15 ohms. So R Thevenin is 10 in parallel with 15, or 6 ohms. So L is going to be 6 ohms times 2 seconds, or 12 Henry. To find Vs1 and Vs2, we're going to use these two things. If you look at the circuit before the change at 0, the value of the voltage source is Vs1, 10 ohm resistor, 15 ohm resistor. The inductor is going to be a DC short circuit. IL of 0 minus we get from the plot, to be 0.4 amps. Because of this short, no current is going to flow through the 15 ohm resistor, and so we get from Ohm's law, IL of 0 minus, which we know, is simply Vs1 over 10 ohms. So from that we get that Vs1 is equal to 4 volts. Likewise, as t approaches infinity, we are once again in a DC steady state situation. But now the value of the voltage source is Vs2. We still have the 10 ohm and the 15 ohm resistor. IL of infinity is 0.2 amps. So using the same argument as before, Vs2 then is going to be 10 ohms times 0.2 amps, or 2 volts. By the way, if you look at our original sketch of the source, we had it going up like this, not really knowing ahead of time what Vs1 and Vs2 would be. In actuality, it looks like this. And if we were thinking when we first sketched this here, if you looked at this response here, you could probably have guessed that Vs1 had to be higher than Vs2. But it really doesn't matter. It comes out once we do the problem. The last topic in this packet of notes is dealing with circuits with multiple abrupt changes. So the idea here is, what if you have a change not just at one time, 0 usually, but what if you have multiple changes? This happens a lot in switching circuits or clocked circuits. Switching or clocked circuits. Well, the procedure for solving these transient circuits is really not that much different from doing it with just a single change in the circuit. What we do is, if you have multiple changes at T1, T2, T3, etc., the way you do it is you solve the circuit assuming just the first change at T1. So suppose here we get something like this, and our transient response might look something like that. And whatever equation we come up with is actually valid only between T1 and T2. T2 is when the second change kicks in. When the second change kicks in, the response, the transient response, is going to change its shape. What you do here, you evaluate the original equation at the point of the second discontinuity. This becomes our new initial condition. And then from this new initial condition, we can determine what the response would look like. But if there's another change at T3, we evaluate this second function at the point of the third discontinuity. It becomes yet another new initial condition, and we can now, from this point, determine what the response would look like. And of course, if there was another change at T4, let's say here, for example, you would get another initial condition. Anyway, when it's all said and done, the final response, it's going to be this blue line between T1 and T2. It's going to be the red curve between T2 and T3, and it's going to be the green curve after T3, and we get that. So let's do a couple problems to illustrate this idea. You also want to look in the book at example 7.6. They also do a problem there. So this is a very simple circuit. It's a capacitor, a single resistor, and a voltage source Vs. Vs, in this case, is what we call a pulse. So Vs of t is some constant Vs times u of t minus t1. Let's see what this shape looks like. So u of t starts at 0, goes to 1 at time 0. U of t minus t1 starts at 0 and goes to 1 at time t1. So Vs of t is this first figure minus the second figure times the constant Vs. So Vs of t looks like this there, where that value is Vs. And this is called a pulse signal. So let's try to think about what's happening to the voltage across the capacitor. Before 0, it's going to be 0. At time 0, when the pulse turns on, the capacitor is going to start charging. We'll start getting charges deposited on the plates of the capacitor. But it doesn't catch up to Vs of t immediately. It's going to be exponentially get up there. And we don't know how long it's going to take. Depends upon the time constant, but eventually it would get up to Vs of t. But what happens here, so this is a charging capacitor. But what happens is at T1, perhaps before the capacitor had a chance to fully charge, the pulse signal turns off, and now the capacitor is going to discharge. And so the total shape of the voltage across the capacitor is going to look something like that. On the next page, we're going to come up with an equation for Vc of t. Okay, we see that the first change in the circuit is at t equals 0. What's happening here is the capacitor charges from 0 volts all the way up to Vs volts. So if you think about the equation for the voltage across the capacitor, it's going to be Vc of infinity plus Vc of 0 minus Vc of infinity times e to the minus t over tau. If you plug in the values here, it's going to be Vs plus 0 minus Vs e to the minus t over Rc, which we could rewrite as Vs times 1 minus e to the minus t over Rc volts. This expression is not valid from 0 to infinity, though. It's only valid between 0 and T1. So at t equal T1, we have another change in the circuit. So we need a new initial condition. The new initial condition is just Vc of T1 minus. Vc of T1 minus, you basically plug T1 into that expression there. Vc of T1 minus is just Vs times 1 minus e to the minus T1 over Rc. And this also has to be Vc of T1 plus. Why? Because the voltage across the capacitor cannot change instantaneously. And I should point out here, this is just a number. T1 is going to be a number, and so this expression is just going to be a number. And then for t greater than or equal to T1, what we're going to see is the capacitor discharges from its value at t equal to T1. So Vc of t is going to start out at Vs times 1 minus e to the minus T1 over Rc. Once again, this is just a number, times e to the minus t minus T1 over Rc. Note that because the discontinuity is not at 0 anymore, we need the t minus T1. We can put these two expressions together to get a final expression for Vc of t. We had DC steady state before the pulse turns on. Then between time 0 and T1, we had a charging capacitor. And then for time greater than T1, we had a discharging capacitor. One thing to point out, here t is a variable, here it is a number T1. So if we go to plot this, first off, let's plot the pulse itself. We saw this from the previous page. Here's the input pulse. What we're going to see is that the actual shape of Vc of t depends on the relationship between the time constant and the pulse width. The pulse width is just this number T1. So the pulse width is how long this pulse is high. If the RC time constant is of the order of the pulse width, we'll do that in red. That's going to be this type of situation. So Vc starts at 0, it rises, but once again, before it gets a chance to get up to its final value, it's going to start discharging. Suppose the time constant is much less than the pulse width. We'll do that one in green. What happens here, once again, it starts at 0, it starts charging, but now because the time constant is so short, it gets a chance to reach its steady state value before the pulse turns off. So in this case, the capacitor voltage much better matches the source voltage. In the third case, suppose the RC time constant is much larger than T1. We'll do that one in black. As in the previous two cases, the voltage across the capacitor starts at 0. But now, as it starts rising, it's not going to get anywhere near its final value before it starts discharging. So what we see here in these three situations is that the actual shape of VC depends very, very much on the relationship between the time constant and the pulse width. So where is this important? This is important in digital circuits or any type of clocked circuit. What you want is you want the time constant of the circuit that you're driving to be very, very small with respect to the clock, because otherwise the circuit cannot keep up with the clock speed. So the bottom line is you want your time constant to be as small as physically possible so that you have a situation more like this green one here rather than the red or the black situation. Let's do one final example. So here we have a circuit that at time 0, we're going to start charging a capacitor with a 24-volt source. And then at time equal 5 seconds, we're going to now switch in another resistor. So we're not adding or deleting a voltage source at time equal 5 seconds, but we are changing the circuit. So we're basically going to have 3 different regions of time. We have t less than 0, that's going to be DC steady state. Then we're going to have the time between 0 and 5 seconds. And finally, we're going to have time greater than 5 seconds. So for t less than 0, once again, that's our DC steady state. It's a pretty boring circuit. It's just a capacitor sitting by itself. So its voltage, V of 0 minus, is just 0 volts, which also means that the voltage across the capacitor at 0 plus is going to be 0 volts. Between 0 and 5 seconds, we have a circuit that's going to look like this. 24-volt source, 16 kilo-ohm resistor, and a charging capacitor. It's going to start charging. If it was allowed to get to infinity, the voltage across the capacitor V at infinity would be 24 volts. And the time constant, we're going to call it tau sub 1 because there are actually 2 different time constants in this circuit. The time constant is just 16 kilo-ohms times 250 microfarad or 4 seconds. So the voltage across the capacitor V of t is V of infinity plus 0 minus V of infinity times e to the minus t over 4, which you can rewrite as 24 times 1 minus e to the minus t over 4 volts. And once again, this expression is valid only up to 5 seconds. The voltage across the capacitor at 5 seconds then is 24 times 1 minus e to the minus 5/4, or 17.12 volts. So we see that by the time this second switch comes into play, we have not reached our DC steady state. We're only up to 17.12 volts. So for t greater than or equal to 5 seconds, we now have a circuit that looks like this. This voltage source is still present. This resistor is still there. The capacitor is still there. But now we have an additional resistor. The addition of the second resistor is going to cause two things to happen. First off, it's going to change V of infinity. The voltage across the capacitor is no longer going to want to go all the way up to 24 volts. The second change is the time constant is going to change because the resistance seen by the capacitor is no longer just 16 kiloohms. So V of infinity now, we're going to see, is 12 volts. How do we get that? 24 volts, 16K, 16K, and the capacitor eventually looks like an open circuit again. So from voltage division, V of infinity is actually 12 volts. Our new time constant we get from finding the Thevenin resistance as seen by the capacitor in this situation. Now that we have two resistors here, if you look at the resistance as seen by the capacitor, we now have these two 16 kilo ohm resistors in parallel. So our new time constant, I will call it tau 2, is now going to be 8 kilo ohms times 250 microfarad, or 2 seconds. So V of t for this range here, and that's supposed to be seconds. So V of t here is going to be voltage at time infinity plus the initial value, which is now 17.12, minus infinity times e to the minus t minus 5 over 2. We can put this together. We have our three distinct ranges. The voltage across the capacitor is going to be 0 volts before the first change in the circuit. This is our DC steady state. Then it's going to start charging up to 24 volts. With the time constant of 4 seconds. And this is valid between 0 and 5 seconds. Then it's going to be 12 plus 5.12 e to the minus t minus 5 over 2 volts for t greater than or equal to 5 seconds. So if you were to plot this, let's make this 2, 4, 6, 8, 10, 12, 14, 16 seconds. And let's make this 6, 12, 18, 24. So initial voltage across the capacitor is 0. At time 0, it starts charging up to 24 volts, and it would take 20 seconds to get there. Something like that. But before it gets a chance to get to its final charged value of 24 volts, the circuit changes at 5 seconds. And so this becomes a new initial value. It was 17.12 volts. And now it wants to go to a final value of 12 volts. So it's actually above 12, so it's going to start decreasing now. And how long is it going to take? The time constant is 2 seconds, so it's going to take 10 seconds from here. So it's going to take until time of 15 to get to 12 volts. So it'll look something like that. So the final response, uncharged, starts charging at a slower rate, and then it starts charging to the new value, a lower value, at a faster rate. So notice, once again, the introduction of this resistor here causes two things to happen. It causes the time constant to change. Instead of 4 seconds to 2 seconds, it does it twice as quickly. And it causes the final value, rather than being 24, it becomes 12. This ends the packet of notes dealing with RC and RL circuits. Next class, we will start looking at second order RLC circuits. Have a good day.